Hello students, today I'll discuss about linear dependence and independence of solutions of linear differential equations using Wronskian. Now let us see the definition of linear dependence and independence first. To define the linear dependence and independence of solutions of linear differential equation, let us consider a second order differential equation of this type. Here a0x, a1x, a2x are all continuous in an interval ab and a0x non-zero for each x in the open interval ab. Say this equation 1 has two solutions, y1x and y2x. Now for linear dependence, the two solutions y1x and y2x of the differential equation will be linearly dependent if there exists two constants c1 and c2 not both 0 such that c1 y1x plus c2 y2x is equal to 0 for each x in the open interval ab. And the same solutions y1x and y2x will be linearly independent if they are not linearly dependent. That is, if c1 y1x plus c2 y2x is equal to 0 implies c1 0 and c2 equals 0 for all x belong to the open interval ab. Now the definition of Wronskian. For the same solutions y1x and y2x of the differential equation 1, the Wronskian is denoted by wx or wy1 and y2 and is defined as the determinant of y1, y2, y dash 1, y2 dash. As it's a second order differential equation, so to determine the Wronskian, we need to find the derivatives up to first order. And the same definition we can extend up to the nth order differential equation. Now let us look at a theorem which states the two solutions y1x and y2x of the differential equation a0x y double dash plus a1x y dash plus a2x is equal to 0, where a0x non-zero and x belong to ab, are linearly dependent if and only if their Wronskian is identically 0. This theorem is helpful to determine whether the solutions of the differential equation dependent or independent. Next, we will look at the proof of the theorem. To prove the theorem, we will make use of these two remarks. Remark 1, if yx is a solution of this differential equation satisfying the conditions y at x0 is equal to 0 and y dash x0 is equal to 0 for some x0 in the open interval ab, then yx is identically 0 in the interval ab. And the remark 2, if y1x and y2x are any two solutions of this differential equation, then the linear combination c1 y1x plus c2 y2x, where c1 c2 are any constants, is also a solution of the differential equation. Now let's see the necessary condition proof. Let y1x and y2x be two linearly dependent solutions of the given differential equation. Then we will try to prove that the Wronskian is identically 0. So as we have considered here y1x and y2x are linearly dependent, therefore by the definition of linear dependence, we will get two constants c1, c2 not both 0 such that c1 y1x plus c2 y2x is equal to 0. Let's consider this as 1. Now differentiating 1 with respect to x, we have c1 y1 dash x plus c2 y2 dash x is equal to 0. Let's take this as number 2. As the constants c1 and c2 are not both 0, that means this system of solutions have a non-zero solution. So for this, we must have y1x, y2x, the determinant y1x, y2x, y1 dash x, y2 dash x is equal to 0. And this part is nothing but, by the definition of Wronskian, this is Wronskian of y1, y2 is equal to 0. This is for all x. Hence, the Wronskian is identically 0 for all x in the interval AB. Now, let us prove the sufficient part. Suppose Wronskian of the two solutions y1x and y2x is identically 0. That is, wx is equal to y1x, y2x, y1 dash x, y2 dash x is equal to 0. Wronskian is equal to 0. We will try to show that the solutions y1x and y2x are linearly dependent. As this Wronskian is identically 0, therefore, for some particular value, say x0 in the open interval, wx0 is equal to y1 x0, y2 x0, y1 dash x0, y2 dash x0 is also 0. Wronskian identically 0. It is identically 0 means what? It is for all x in the open interval AB. Hence, for any particular value belong to that open interval, we will get the same is equal to 0. Let's take this as number 4. Now, from the condition 4, we can find two constants, say k1 and k2, not both 0, such that k1 y1 x0 plus k2 y2 x0 is equal to 0. Let's take it number 5. And k1 y1 dash x0 plus k2 y2 dash x0 is equal to 0. Say equation number 6. Now consider yx is equal to the linear combination of the solutions y1x and y2x as k1 y1x plus k2 y2x. As yx is the linear combination of these two solutions, so by remark 2, yx is a solution of the given differential equation. Say this equation is number 7. Now from 7, using the number 5, we have y at x0 is equal to k1 y1 x0 plus k2 y2 x0 is equal to 0. This is using 5. Now differentiating equation 7, differentiating equation 7 with respect to x, we have y dash x is equal to k1 y1 dash x plus k2 y2 dash x. Now over this, if we apply number 6 equation, then we have y dash at x0 is equal to k1 y1 dash x0 plus k2 y2 dash x0 is equal to 0. Thus, we find that yx is a solution of the differential equation such that y at x0 is equal to 0 and y dash x0 is equal to 0. Hence, by remark 1, y at x is equal to 0 identically in the open interval AB. And so, by that equation 7, k1 y1x plus k2 y2x is equal to 0 for all x belong to AB and as here k1 k2 are both not 0, therefore the solutions y1x and y2x are linearly dependent. That means considering Wronskian identically 0, we have proved here the solutions y1x and y2x of the differential equation linearly dependent. Hence the sufficient part, hence the proof of the theorem. Let us look at another theorem relating to the linear independence of solutions of differential equation. This theorem states that the necessary and sufficient condition for the two solutions y1x and y2x of the differential equation of this type, where p1 and p2 are functions of x or constants, are linearly independent, is that the Wronskian does not vanish identically. Though we have defined the linear dependence, independence and Wronskian as well as the proofs only for the second order differential equation, those can be extended up to nth order differential equation also. Now let us look at few examples. Example 1. Test the linear independence of the solutions y1x is equal to sin x and y2x is equal to cos x of this differential equations. So that means we have to test the linear independence of this solutions of this equation. So let us consider the Wronskian of the solutions. As per definition of the Wronskian for two solutions, we have determinant of y1x, y2x, y1 dash x, y2 dash x. So y1x it's given sin x, y2x is cos x, y1 dash x, so just differentiate sin x with respect to x giving cos x, y2 dash x differentiate y2 with respect to x giving minus sin x. It's simple calculation, just evaluate the determinant, it will be minus sin square x minus cos square x. So minus of sin square x plus cos square x, which giving minus 1, a constant. It will never be 0, hence Wronskian is identically, does not finish identically. That means the solutions y1x and y2x are linearly independent. Are linearly independent, as Wronskian does not finish identically. Now let us look at another example. Test the linear independence of the functions, this time three functions there, 1x, x square. Solution, let us consider y1x1, y2x x, y3x x square. So Wronskian of the functions will be as three functions there. So y1, y2, y3, y1 dash, y2 dash, y3 dash, y1 double dash, y2 double dash, y3 double dash. In the similar fashion, we will try to calculate this. y1 it's 1, y2 x, y3 x square. First derivative constant 1, 0, y2 dash that is 1, y3 dash it is twice x. Next second derivative of the functions, 0 is 0, second derivative is 0, then 2. Now just we will find the determinant. So 1 into 2 minus 0 into twice x, so 0 plus x, 0 into twice x minus 0 into 2 that is 0 plus x square, 0 into 0 minus 0 into 0, so 0 that part. That means we have 2, 1 into 2 after simplifying this part, again non-zero. That means what we have here, Wronskian does not finish identically, therefore the functions 1x, x square are linearly independent.